let's talk a little bit about aromaticity and look at some molecules and the rules for what makes them aromatic or not. So one, aromaticity is, in the simplest way of thinking about it, a really strong form of resonance. So if we fulfill the rules to be able to call something aromatic, it's resonance stabilized, but a lot more resonance stabilized than it typically would be. So if molecules fit these criteria, then we can call them aromatic, and they are particularly stable compounds. So the electrons are shared really well and enough to make them stable and not very reactive. So aromaticity, one of the things you need is a cyclic pi electron system. And so there's a bunch of ways to get that, but it has to be a ring structure, right? So even if you have a lot of resonance, right, it's not in a ring, it's not going to be aromatic, right? So it has resonance stability there and can share as a conjugated system, but it can't be aromatic. It has to be a ring, right? Benzene is the simplest example of that. And what I like to do to keep track, because sometimes it's easy to see, sometimes it's not, but it's always helpful, is, all right, so every atom all the way around the ring has to have some pi electrons or a lone pair or a positive charge in order for that electron system to flow through. Right? So this carbon atom is one part of a pi bond. This carbon atom is the other half of the pi bond. Right? So yes and yes, these two carbons can share those electrons. Another pi bond, another pi bond, another pi, all the way around each atom in the ring is part of that pi system, so those electrons can flow around, so that we have a cyclic pi system there. Right? So looking at an example like this, you might think, all right, so this looks a little different. Right? So I have an atom here and here that are part of a pi electron bonded system. I have a lone pair of electrons. If those share, that's okay. Right? We can look at in another video of when the lone pairs count and when they do not. But if those lone pairs there can be part of that pi sharing system, another carbon atom, part of a double bond, another, but then this last one does not. Right? So the carbon atom on the bottom of the ring interrupts that electron sharing. So even though there's resonance and we can draw some resonance structures, it doesn't cycle all the way around. So it can't be aromatic, right? So it has to be a cyclic system of pi electrons. It has to be planar as well, which you can't really tell by drawing structures. So we draw a lot of our rings flat on the board anyway, but planarity is important for those systems to be able to share. So essentially, if you've got carbon-carbon bonds, right? So I'm just drawing an example, thinking about what's going to break up this electron sharing. Well, even if each of these atoms is part of a conjugated pi system, right, my pi electrons are up here in these other positions. Right, so if everything is flat and in the same plane, and this, I know I'm not drawing a ring here, if everything is flat and in the same plane, then these are aligned in a way where the electrons can flow through and share. Right? If you bend that out of shape, though, like a typical conjugated system, you can run into some troubles with bond rotations. If I bend that out of shape, then essentially I'm changing that gap there. I'm not allowing those to share. The electron systems aren't able to interact in the same way. So even if it might look like they can share all the way around, if there's a bend or a kink and it's not planar anymore, it breaks up the ability for those electrons to share evenly. So it has to be planar. When in doubt, build a model. Right? That can be really helpful to figure out if something's planar. It also has to have an odd number of electron pairs. So aromatic structures that have this unusual stability always have the same sets of electron pairs. So if I'm counting whether or not I have cyclic pi systems, I'm looking for parts of a pi bond, I'm looking for lone pairs. It can also be a positive charge as well. That is not a set of electrons, right? There's no electrons there, but it kind of acts as an empty space for electrons to share, right? So if you have an empty p orbital, right, this would be sp2 hybridized, then I've got a room for those electrons to flow through. So a weird structure like this, I've got pi electrons on this carbon, pi on this carbon, plus charge here. That works. That's a cyclic pi system. And now we want to count electron pairs, and then odd numbers work. So this one has one pair. Nothing here. So that works. Right? This molecule here is a little different. So I've got sharing throughout for the same reason here. I've got a positive charge, which allows the electrons to mix. But I got 1, 2. Right? So that's an odd number of electron pairs, and that won't be an aromatic molecule. Same here. Cyclic system throughout, 1, 2, that's not aromatic. And then, of course, benzene, 1, 2, 3. Right? Odd number of pairs, right? Not total electrons, but electron pairs. Right? So that would be aromatic as well. Right? So for hydrocarbons especially, that's what we're looking for. Planarity can be a little bit tricky, but you can always build a model to try and test it out. But we're going to look at every atom around the ring, and does it have something that can share electrons? Does it have a lone pair? Is it part of a pi bond? Does it have a positive charge? Right? That's how we can tell if something's aromatic or not.